Great. So let's just do a quick review of last time and spend a little bit of extra time on the active versus passive transformations, which will be relevant for reviewing the active versus passive transformation, will be relevant for what we're talking about today. So last time we talked about the explicit time evolution of states in the propagator. We said that for a Hamiltonian that's time independent, the time evolution operator is quite straightforward, which tells us how to evolve our state from some initial time to some final time. And we said that we can make progress on this expression, where I say make progress because we don't like operators, we like complex numbers, or at worst complex numbers. And so we insert a complete set of states in terms of the energy eigenstates, which we know exists because the Hamiltonian is Hermitian. And so we can talk about the time evolution of the coefficients in the basis of the energy eigenstates. Alternatively, we can insert a 1, and we can try to find the time-dependent wave function at some future time based on the time-dependent wave function at the initial time, integrated over position with this object here, which we call the propagator, and as was cleverly pointed out, is extremely reminiscent of a Green's function, and we'll talk about that more today. And then we did an explicit example of computing the propagator for the free particle, and we obtained a certain expression. One comment, if you work it out, and in the land of infinite time to give you infinite homework problems or infinite numbers of homework problems, I would have you explicitly show that the argument of this exponential e to the I, this is the classical action. This is the action that the particle would pick up going from x prime to x in time t. And that should be sort of it's a foreshadow. Okay, we talked about the connection between time and mechanics, where the trace of the time evolution operator evaluated at -I 1 over time, or rather 1 over temperature for the time, gives us precisely the partition function. Okay, so that's a breeze through before we get to active passive transformations. Are there any questions on any of that before we continue? Great. So active versus passive transformations, we said that we can think of a symmetry transformation in 2 equivalent ways. So the first is an active transformation, where the system itself is transformed while we leave the coordinates invariant. That's kind of the more straightforward, obvious, intuitive way of transforming some system. We also talked about a passive transformation, where here the coordinates are changed while the system is left unchanged. So I always find the visualization to be helpful in terms of active versus passive. So we think about having some function f of x, it's sort of lumpy, so that gives us some structure for us to hang our hats on, and say this function is maximized at some position x0 as a function of x. And we want to propagate this function to the right by an amount a. So the first thing that we might do is an active transformation, where we actively transform f of x to a function f prime of x. The x is being the same, it's the same coordinate system, but the f is changed. So explicitly, now in our coordinates, our x coordinates, we have our original function f of x, and we now move it to the right by an a, such as now this f prime of x. So the peak of f of x was at x0. Now the peak of f prime of x is at x0 plus a. It has been moved to the right by an amount a. And so what we would like to understand is, how can we write f prime of x in terms of f of x? And the point is that f prime of x is equal to f of x evaluated at a different point. And in particular, and I always, as I said, I always get this sign flipped up, so I always just have to work it out in my head, that if f of x is peaked at x0, f prime of x is peaked at x0 plus a, so it needs to be a minus a here, so that when I put in x0 plus a for x, I get x0 plus a, I subtract the a, and I get f of x0, which is where f is maximized. Okay, and so in terms of the translations, what this is saying is that f prime of x is f evaluated at the inverse transformation acting on the coordinates. And you saw this in your homework with the rotations. Good. And so we could say in general that our f prime of x for some general transformation t of theta a is f of t inverse theta x. All right, super. Questions on the active transformation? Great. So the passive transformation is now we leave the function alone. So we've got our red function f of x, and our f prime of x prime is exactly the same. But now we change our coordinate system. So our coordinate system was the x coordinates, and now we move our coordinates to x prime, where again we have that the peak of our f prime of x prime is at x0 plus a, so it's moved to the right. And how are these functions related? As I just said, f prime of x prime is equal to f of x. And we said that x prime is the translation of x is x plus a. And so then we get f prime of x prime is f prime of x plus a equals f of x. And so now in the passive transformation, we have our f prime of the transformation on x is equal to f of x. Good. And then we said, if I rename this translated x to some kind of x prime, then this is f prime of x prime equals f of the inverse on x prime in a self-consistent way between active and passive. Got nods. Any questions anywhere? Yes.
On the line before you write for any general transformation, you have f prime of x prime equals f of, and then the engine subtraction. Isn't that just supposed to be the first x without a prime? Because f prime of x prime equals just f of x.
Okay, let's try this again. So I have that.
Oh, never mind. Misunderstood.
Okay, great. It's not easy. Good. Last questions. All right, great. So let's now here. Okay. Dangerous. So let's now talk about active versus passive transformations in quantum mechanics. And we talked about leading towards the Schrödinger picture and the Heisenberg picture, which I gave you a qualitative discussion of last time. All right, so in quantum mechanics, the state of the system is represented by a vector, which is, it's really a ray in a complex Hilbert space. So we have some psi ket, which is in some h. And the, in air quotes, coordinates that we use to describe the state are a basis that we choose for our Hilbert space. And generally, we choose a CON, complete orthonormal basis, associated with and parenthetically essentially self-adjoint operator, such as position or momentum. Or say energy. So we may perform an active transformation on a state psi, say some psi ket, by acting on that psi ket by a linear unitary operator, okay, or anti-unitary, but for our class, linear unitary operator representation of a symmetry transformation. So for example, the translation, translation by A, that's what we talked about in the specific example of that f of x goes to f of x minus A. So translation by A on our psi ket is achieved by, okay, so I have some new vector in my Hilbert space, psi prime, which is given by the translation operator. So it's some unitary operator associated with the momentum operator, which is the generator of translations. And I'm translating by a distance A, and this operator is acting on my initial state. And we know that this is given by e to the minus I a p hat psi. And if you wanted to make further progress, you could insert a complete set of momentum eigenstates, for example, and if you had then the initial momentum space representation of the state, then you'd be able to do some integrals and explicitly figure out what the state is in the translated state in the old momentum basis. Okay, so making connections back to this active and passive transformations that we just mentioned, I could ask, what is the amplitude associated with this new state? Right, I'm asking, what is this state in the old coordinate system? I'm not changing the coordinate system. Well, I just plug in what we just said. So this is x, and this is the UPA acting on the state psi. Now, again, to make contact back with the active versus passive transformation, I could now think, instead of acting the unitary operator on the state psi, I could think about the unitary operator acting on the basis state x. And when the dust settles in terms of the various signs, this is x minus a on psi. And so what do I call this amplitude? Yeah, exactly. It's psi of x minus a. And isn't this exactly what we said before? I had f prime of x is f of x minus a. So it's exactly analogous. Okay, great. And for a general transformation, some transformation depending on some parameters with associated generators, J vector hat. We have psi prime is U J theta A on psi, and psi prime of X is going to be equal to psi of the inverse transformation on X. I feel like that generalization is straightforward, but let me pause for any questions on that or anything else that I've talked about so far. Okay.
Can you hear me?
Let's now talk about passive transformations. So for passive transformations, so we're going to perform a change of coordinates. What are coordinates in quantum mechanics? The coordinates are the basis. So performing a change of, in air quotes, coordinates, which is a change of basis. And what is a change of basis? Change of basis in mathematical terms is known as a similarity transform. I think I've mentioned this before at some point. We used to like you to have, I would like to believe that you have heard the word similarity transform before, I'm deeply tempted to go through the videos. It's fine. It's fine. Whether you have heard it and you don't remember, or whether I didn't actually tell you is irrelevant because you don't remember it. At the end of the day, you don't remember it. But okay, so similarity transform is just a set of words that I think, set of words you should be familiar with. What does it mean? So our basis is defined by the eigenkets of an operator. Call it in general O hat, so it could be X hat, B hat. And the similarity transform is given by, so in general, my O hat prime is defined as the inverse unitary operator for the symmetry transformation. And then my O hat, I'm going to try to make my thetas clearly different from my O's. So my O hat and then my transformation, again, theta A so far. And I guess I would like, in principle, for you to have heard of similarity transforms and change of bases in the context of linear algebra. if you have matrices, what does a matrix look like in a particular basis, and then what does that matrix look like in a different basis? And what you do is exactly this. You have some unitary matrix, and then you have the inverse of the unitary matrix. And that in general is a similarity transform in the context of finite dimensional linear algebra, which I would again sort of hazard that whoever taught you linear algebra taught you this at some point. I could easily imagine it went, or in what year one year out the other. I feel like that happened with me when I took linear algebra from the math department at some point in my life. Nevertheless, it's an important concept. The similarity transform is an important concept. Yeah, it's an important concept. We're going to harp on it quite a bit here. Yes.
Kind of looks like a diagonalization. So anything to do with that, or is that just supervision?
The diagonalization is basically finding a basis for which your matrix looks nice.
Okay.
So diagonalization is a change of basis. Yeah. So it is very similar. So nice. Great. Other questions? Okay. Super. So at the risk of doing some of your homework for you, I realize now when I was looking at this with clear eyes. So let's see how, I guess I'm calling this one. One works for a translation to the right by A. So we'll have that our position operator prime is e to the I A momentum operator, original position operator, e to the minus I A momentum operator. So this is just a straightforward application of one. I assume no questions on that. However, now we need to compute this, and that's a rather nasty looking thing. So to evaluate two, we will be aided by a form of the Baker, Campbell, Hausdorff lemma, which I imagine you have not heard of before. Not again. So this is a very widely used tool in quantum mechanics. Not unreasonable for you to have not seen it before, but try to remember this. And I guess you'll remember it because we'll be using it a number of times. So if I have some e to the I lambda x operator, y operator, e to the minus I lambda x operator, this is e to the I lambda commutator operator x with an open slot acting on the y operator. So this right-hand side is a rather nifty shorthand, which I will define here. So it's exponential, Taylor expansion of the exponential. The first term is just a 1, so I get a 1, and then the y operator. And then the first term is linear, and it's the x operator commutator with y. I'm slotting the y into that open space in the exponential. And then the second term is your usual minus a half lambda squared from the I lambda. And then I have a commutator of x slotting into what came before it, which is the x commutator with the y. And then plus so on and so forth. Can you see what will happen with the third term? What will the third term be? Yeah, so it'll be x commutator with x commutator with x commutator 1. Yeah, okay, great. Super. So is it clear immediately then what the result for 2 will be using this BCH lemma? So what will the first term be? Very good. So x prime is going to be x, and then what's the next term? Okay, so it's going to be plus IA commutator of x with p, which is good. And then what's going to happen with the second order term? I'm sorry? It's going to be 0, right? Because it'll be the commutator of momentum with just 1. And all the other higher order terms are 0. All right, great. So this is already looking very promising and very familiar. Therefore, we have that. So I want to see this in the passive transformation, right? So we know this is the expression that we have from when we talked about the f prime of x prime is equal to f of x. And this psi prime of x prime, this is x prime psi prime. And on the right-hand side, we have x psi. And then what I then wrote in my, when I was preparing this, is my x prime is x plus a psi prime. And this is also x plus a psi. What the fuck am I doing? This is all garbage. Sorry. This is x psi. And so this is psi prime of x plus a equals psi of x. All right. I've managed to confuse myself. I apologize. We'll correct that next time. All right. Let's erase this from all of our memories. All right. It will work. Not here, obviously. All right. Expectation values. Yeah, I'm sorry. So what I was trying to do is I was trying to make the connection back to what we did before with active and passive transformations. So we had active and passive transformations, which I think is here. So with the active transformation, we saw nicely that f prime of x equals f of x minus a. And we saw that that worked correctly in terms of our amplitude, right? That we got that psi prime of x is equal to psi of x minus a. What I wanted to make a connection back to was that in my passive transformation, my f prime of x prime is equal to f of x. And so what I was driving towards was this expression here, really that psi prime x prime equals psi of x. And we said, so this x prime, the claim is that this x prime is x plus a. And then we just have x on the right-hand side. And so the right-hand side trivially becomes psi of x, and the left-hand side becomes psi prime of x plus a. And so we get, again, a consistency relation. Yes. %, yeah. And the emphasis that I'm trying to make, and I'm sorry, I've managed to confuse myself with primes, is that, and this is a key point, in a weird way. So in our active transformation in quantum mechanics, our states are changing, but our basis states are not changing. Why are our basis states not changing? Because our basis states are the eigenkets of the operators. So we're performing the transformation on the states, not the operators. However, in complete analogy with active and passive transformations, instead of performing the transformation on the states, we could perform the transformation on the operators via similarity transform. And because our coordinates are the basis vectors, and the basis vectors are the eigenkets of operators, by performing a transformation on the operator, we're performing a transformation on the eigenkets. And we're therefore forming a transformation, excuse me, on the basis states, and that's what a passive transformation is. So those are the key messages, where what should have been nicely straightforward was that our psi prime of x prime equals psi of x. So this is what we have in a passive transformation, and it comes through in a natural way in the quantum mechanical setting. The psi prime of x prime is the inner product of x prime with psi prime, and the psi of x is the inner product of x with psi. And what I managed to not explain well is to convince all of us that this x prime bra is really the x plus a bra. And that then tells us that this is the psi prime of x plus a, and the right-hand side is psi of x. Okay, good. And we'll see this again in the time evolution, and hopefully in a way that is more clear. All right, so we have that. So I'm going to say we have. So we have that amplitudes don't change, or have that amplitudes transform exactly as in active versus passive transformations. Or functions. And we can equivalently also usefully consider expectation values in active or passive transformations. So the expectation value of some operator in our symmetry transform system. So this is equal to the transform state, the transformed operator, and the transform state. And we can think about this expectation value in two equivalent ways. Where I can think about either my operator being untransformed, i.e. an active transformation, and my states being transformed. So I have my unitary operator acting on the state to the right, and my inverse unitary operator acting on the state to the left. Or I could think about my states being unchanged, and rather these unitary operators performing a similarity transform on the operator. So I can think about this as the unitary operators acting to the left and right, where this is an active transformation. Or I could think about the similarity transform as a passive transformation. Yes.
When you say the amplitude of function, are you talking about square modulus sine? Or...
No, so the probability is associated with the square modulus of the amplitude, but I'm really talking about the amplitude.
Oh, yeah, so just the modulus. Oh, when you say the amplitude of a function.
Or I'm sorry, the amplitude of the state. So here I'm talking about, I have an amplitude.
Yes.
Right. So I have some state, which is some psi ket.
Okay.
I can ask, what does that state look like in a particular basis? So like the x basis. And so this is just some complex number, which I call an amplitude. And if I take the modulus squared of this, it tells me about the probability of finding my particle between x and x plus dx.
Okay.
Okay, great.
Yeah, why is the sign on the? Never mind.
Okay, good. Other questions? Okay, great. So let's modulo my fumbling of the passive transformation there. Let's apply this to time evolution. Okay. So we could think about any symmetry transformation as active or passive, i.e. The transformation to the unitary transformation acting on the state or on the operator or operators, I should say. And so this translates over to time evolution. Time evolution is a symmetry transformation. So we think of an active transformation. So I guess we call an active time translation that's working in the Schrödinger picture. And this is what you've been doing all your quantum mechanical lives. So we say that psi as a function of t in the Schrödinger picture is the time evolution operator acting on the state at the initial time, again, in the Schrödinger picture. And if we have some operator that has no explicit time dependence, which is in the Schrödinger picture, then this operator at some later time is exactly the same operator at the initial time. And we call a passive time translation as working in the Heisenberg picture. So here we have that our state psi as a function time in the Heisenberg picture is equal to the initial state in the Heisenberg picture, while our operator in the Heisenberg picture at time t is related to our operator at the initial time in the Heisenberg picture by the similarity transform. So I feel like that's a very straightforward bringing over what we just talked about. But let me just pause because this is a very important set of words that we're going to need to understand and then apply. One thing that often comes to mind as a question is, well, when does an operator depend on time? You could have, for example, a Hamiltonian that depends on time because you have some, like you're an electron in a time-changing magnetic field, for example. Something like the position operator, the momentum operator does not generally have explicit time dependence. Good. All right, so notice that both pictures coincide at t equals t0. There's no time evolution has occurred. So we have that psi at t0 in the Schrödinger picture is psi at t0 in the Heisenberg picture, and our operator at t0 in the Schrödinger picture is our operator at t0 in the Heisenberg picture. Maybe another subtle difference to my time evolution operator is associated with an h hat Hamiltonian, and I'm writing a subscript h to denote the Heisenberg picture, no hat. Good. Okay. Notice further that expectation values are the same in both pictures. I don't think you should be surprised given what we literally just talked about. So if I have the expectation value of some operator at some time t, this is the state at time t in the Schrödinger picture, operator at time t in the Schrödinger picture, state psi at time t in the Schrödinger picture. And we said that in the Schrödinger picture, time evolution occurs on the states. But not on the operators. Notice what's happening here. It's a little bit subtle. So the similarity transform is in terms of inverses. My Schrödinger bra is time evolved according to the Hermitian conjugate of the time evolution operator. But the time evolution operator is Hermitian, not Hermitian, unitary. So I replace my dagger with an inverse, which yields for me the similarity transform. And so then this similarity transform leads to the operator in the Heisenberg picture at time t. But remember, in the Heisenberg picture, the states don't change with time. So the Schrödinger state at time t0 is the same as the Heisenberg state at time t0. I guess I can just make this the Heisenberg state at time t0, and that's not too many steps. But the Heisenberg state at time t0 is the Heisenberg state at time t. And so if I call this, say, the expectation value of the operator in the Schrödinger picture on the left, I now have very clearly the expectation value of the operator in the Heisenberg picture at time t on the right. Pause there for any questions.
Whoops.
I'm very sorry, yeah, there's a lot of subscripts floating around, which the intention is for it to be clear. Yeah. Yes.
The last line and the second to last line. I'm sorry to explain this, but why do we have T?
That's the difference between the two pictures. So.
Oh, that's literally what it's. Okay, sorry.
Yep. Yeah. No, this is good, right? So in the Heisenberg picture, the states don't change with time. So the state at time t is the initial state, while the operators do change with time. Whereas in the Schrödinger picture, the states are actively transformed with the time evolution operator, but the operators are not. Okay, good. Last questions. Excuse me. Okay. So let's understand better time evolution in both pictures. Well, in the Heisenberg picture, really. As you've already spent a lot of time understanding time evolution in the Schrödinger picture. So recall that I partial t of my time evolution operator plus u is the Hamiltonian at time t, time evolution operator t0. Which we know how to solve. For the three cases of our Hamiltonian, right? The Hamiltonian can be time independent, and then it's a trivial exponential plus u. Time evolution could depend on the Hamiltonian could depend on time, but commutes with itself at different times, and so is a trivial e to the minus I integral dt prime h of t prime. Or the Hamiltonian might depend on time and not commute with itself at different times. Then you get the time ordered exponential. Good. Let's call this, I forgot what equation we're up to. So we're in a new section. We'll just call this 1 again. If we take the Hermitian conjugate of 1 of this time, of the Schrödinger equation, what are we going to get? Let's start on the left-hand side. The I becomes minus I, good. Partial t, my unitary operator becomes unitary operator Hermitian conjugate. Yeah, we will get to the inverse in a minute, but let's just leave it as a Hermitian conjugate for now. And then on the right-hand side, Exactly. Very good. So we get a swapping of the order with, again, the time evolution operator getting Hermitian conjugated. And as you say, the Hamiltonian is Hermitian, so it does not change. Okay, good. So let's call this equation 2. Then in the Heisenberg picture, we may compute the time evolution d by dt of any operator that depends on time t. So sorry, this is in the Heisenberg picture. D by dt of time evolution operator inverse t0, Heisenberg picture at time. I guess this is the Schrödinger picture. At time t, and then time evolution operator t0, like so. Because the time evolution operator is unitary, the inverse becomes a dagger. And so then we get, just by product rule, okay?
I'm a little bit confused with the first line.
Sorry, the first line here. This is just the definition. So to be more explicit, oops, sorry. Yeah.
With that T not very equal.
Exactly. No, it's good. All right, great. So our definition, and then we take the inverse to the dagger, and then we product rule our time derivative. And so now let's start plugging things in, and I'm going to start dropping indices because it's just getting to be a lot of writing. If there's any confusion, just let me know. So the time derivative of the, time evolution operator Hermitian conjugated, if I come back up here to equation 2, that's going to be I u dagger h. So I get an I u dagger h os u. And then I'm going to rearrange things just a little bit to make it a bit more clear. I've got the time derivative of my time evolution operator on the right. And so if I look at this, I'm going to get this more or less the same thing, but with a minus I and the Hamiltonian popping out to the left. So I get minus I u dagger operator h u, and then plus u dagger partial t operator u. Good. Now let's do something clever, which is to insert a 1. So let's insert a 1, which looks like a U dagger here. Insert a 1, which looks like a U dagger here. And remember that dagger is the same thing as inverse because we have unitary operators. And so what we have on the left, we have our similarity transform on our operator, and then a similarity transform on our Hamiltonian. And over here we have similarity transform on our operator and similarity transform on our Hamiltonian. And so we get that this is equal to I Hamiltonian, where all of the operators are in the Heisenberg picture at time t, and then our operator in the Heisenberg picture at time t, minus I operator in the Heisenberg picture at time t, Hamiltonian with all of the operators inside of it in the Heisenberg picture at time t, plus, and then on the right side, what we're just going to call the partial derivative with respect to time of our operator in the Heisenberg picture. Which makes sense in the sense that I have a U dagger and a U, so again, a similarity transform. Okay. What does this expression look like to you? Looks like a commutator, exactly. So this is I, commutator of the Hamiltonian in the Heisenberg picture at time t, and then our operator in the Heisenberg picture at time t, plus partial operator Heisenberg picture at time t, partial t. And we said that this, all of this, gives me the time evolution of the operator in the Heisenberg picture. And as I mentioned on Friday, what does this look like to you? With Poisson brackets, exactly. So this is exactly analogous to what happens in classical mechanics in terms of the time evolution of various properties of trajectories being generated by the Poisson brackets of the Hamiltonian with, say, your position or your momentum or any function, whatever you care of. So we have very clearly a structure which is self-consistent with the Dirac quantization condition, where the classical Poisson bracket goes over to the quantum commutator with an I added. Feel like you want a question, want to ask a question. Yeah.
Sorry, I was behind while you were speaking.
Okay.
So then going from the line above the green,
Here.
yeah, to the next one.
Here. So I'm inserting my time evolution I'm inserting a 1, clever 1, UU inverse in terms of the form of UU dagger. And then I'm turning all the daggers into inverses. And so I've got a U inverse HU,
Yes.
which is a similarity transform acting on the Hamiltonian. So that gives me the Hamiltonian, the Heisenberg picture. And then I've got U inverse OU, which is a similarity transform on the O operator, which is then the O operator in the Heisenberg picture. You're welcome. Any other questions? All right, wonderful. Okay, so it might be nice to understand how to take commutators in the Heisenberg picture given commutators in the Schrödinger picture, which is what we're used to. Well, if I consider the commutator of some capital X operator in the Heisenberg picture at time t, with the if I take the commutator of that operator with the operator capital Y, again in the Heisenberg picture at time t, again just dropping indices. If you need me to expand all the indices, let me know. So this is U inverse X Schrödinger U, U inverse Y Schrödinger U, minus U inverse Y Schrödinger U, U inverse X Schrödinger U. The U inverses cancel, and I can bring out to the left a U inverse, and I have the commutator of the X Schrödinger with the Y Schrödinger, and then a U on the right. And I'm sorry, I missed an important previous step. So suppose that the commutator of X operator in the Schrödinger picture with Y operator in the Schrödinger picture is equal to Z operator in the Schrödinger picture. So if I assume that I have that particular commutator in the Schrödinger picture, then in the Heisenberg picture, I find that the commutator of X in the Heisenberg picture at time t with Y in the Heisenberg picture at time t is equal to the Z operator in the Heisenberg picture at time t. Any questions there? So in general, we have that, say, D, some generalized position operator in the Heisenberg picture, which might be some vector. dt is I, Hamiltonian in the Heisenberg picture as a function of, say, various Q's in the Heisenberg picture and P's in the Heisenberg picture, and maybe even some time t, and my Q operator in the Heisenberg picture, that this is going to be equal to partial derivative of the Hamiltonian in the Heisenberg picture with respect to the momentum operator in the Heisenberg picture. And momentum operator in the Heisenberg picture, time evolution, partial H Heisenberg picture, partial Q I.
The Hamiltonian difference, no, Heisenberg.
So suppose we have,
Yes.
there you go, is that enough?
Yeah.
So so you could imagine you have some Hamiltonian in, say, the Schrödinger picture, p squared over 2m. Let's leave off the subscript. So quite a standard looking object. In the Schrödinger picture, these operators would be in the Schrödinger picture, and the Heisenberg picture, they'd be in the Heisenberg picture.
The operators are staying the same.
Uh-huh. However, you do know that the time evolution of the Hamiltonian is generated by the commutator of the Hamiltonian with itself, which is always going to be 0 if it's evaluated at the same time, plus the partial derivative. So any total time evolution of the Hamiltonian is going to be related to only its explicit time dependence. So if I have a Hamiltonian, which is like what I have here, no explicit time dependence, then the Hamiltonian is going to be associated with a conserved quantity. The energy is going to be conserved. The time derivative of the energy is 0. The time derivative of the Hamiltonian total time derivative is 0. But if I had, for example, something more complicated, like I have some external force acting on my system that depends on time, then there'll be some explicit time dependence that will influence the total time derivative of the Hamiltonian. Good. You're welcome. All right. So we have Hamilton's equations in quantum form. And we see consistency with the Dirac quantization condition, which tells us that the classical Poisson brackets need to go over to I commutator. Okay. Good. So what happens to the eigenvectors of operators? So this is where I stumbled the last time, but I think we should be able to not stumble this time. All right. So for operators, say O in the Schrödinger picture, with no explicit time dependence, the base kets do not evolve in time. So we write that the state in the Schrödinger picture, this evolves in time. Oops. But then the operators say, oh, in the Schrödinger picture, omega Schrödinger picture is omega in the Schrödinger picture. On the other hand, are not only different fingers, but if we consider or if we continue to consider the base kets as eigenkets of the operators, then the base kets in the Heisenberg picture must pick up time dependence. This tends to give people some pause, but let's see how it works. So in particular, if our operator in the Heisenberg picture depends on time t, then our omega in the Heisenberg picture also has to depend on time t. So instead of absorbing the parametric time dependence in terms of the state evolving in time, now instead our coordinates are depending on time. Coordinates are depending on time. So we can see this explicitly. So our operator in the Heisenberg picture is a similarity transform from the operator in the Schrödinger picture. Oh gosh. How do I want to think about this? And okay, let's think about it this way. All right, so in the Schrödinger picture, we have our operator in the Schrödinger picture acting on omega in the Schrödinger picture is omega and then omega in the Schrödinger picture. And I'm free to hit this on the left with a U inverse. And then I can always insert a 1. And so I get the operator in the Heisenberg picture, and then I have a U inverse. Omega in the Schrödinger picture is equal to omega U inverse omega in the Schrödinger picture. And so this tells me then that my base ket in the Heisenberg picture is equal to U inverse of the base ket in the Schrödinger picture. Right? And this is analogous to what we've seen before. Remember that in my Schrödinger picture, I have that the time evolution of the state is given by the time evolution operator acting on the state. And what I have here is that the time evolution of my base ket is given by the inverse of the time evolution on the initial value. So if I maybe restore my various indices, So. And so in particular, probability amplitudes are the same in both the Schrödinger picture and the Heisenberg picture, as they have to be. So we have to measure the same thing.
Question with the kit of the omega t, H is our.
Absolutely, yeah, right. Because what happens is for the states, state of my system, I have time evolution forwards, no inverse. And so the eigenkets are evolved with the inverse. And let me just make a couple of statements, and I think it'll become clear. So my amplitude for measuring some eigenvalue omega, given that I am in some state psi at time t, and I'm being consciously ambiguous about whether I'm in the Schrödinger or Heisenberg, because I should get the same regardless. So this is the Schrödinger picture overlap of the eigenket omega at time t with the state psi at time t in the Schrödinger picture. And we said that operators don't change with time in the Schrödinger picture. So the eigenket at time t is the eigenket at time t0, but the state at time t in the Schrödinger picture is the time evolution operator acting on the state at time t0 in the Schrödinger picture. So I'm saying that the state evolves with time. In the Schrödinger picture, eigenket does not evolve with time in the Schrödinger picture, because operators don't evolve with time in the Schrödinger picture. But I could equivalently think about this time evolution operator acting to the left on the eigenket, leaving the state alone. So this is equal to the Heisenberg picture, omega at time t, and then psi at t in the Heisenberg picture, where now I have that the state has not evolved in time in the Heisenberg picture. I guess I could add one more step, which is that this is equal to Heisenberg picture omega of t psi of t0 in the Heisenberg picture. Whereas the eigenket has evolved in time in the Heisenberg picture, because the operators evolve in time in the Heisenberg picture. Yeah.
I'm just gonna think about this notation, like start of this, it's A of something.
See, amplitude associated with measuring the quantity omega. So like measuring that my energy is 13.6 eV. And the amplitude, remember that the probability, maybe this will be helpful. So the probability of measuring omega given my state psi at time t This is equal to the modulus squared of this amplitude given psi at time t.
Okay. Why do you put a vertical line next to the omega comma?
That's a conditional probability, usual notation.
Okay.
It's a probability of measuring a theory of getting a thing given that.
Thank you.
Yeah, you're welcome. Okay. Any questions on any of this? Okay, great. By myself the order of operations. I think I know what I'm doing. Good. Very good. So we got 10-ish minutes left. Let's make, so, okay. That's the end of Schrödinger picture versus Heisenberg. We're going to move on to Green's function theory, propagators, resolvents, which will probably, well, I'd be shocked if we finished it today, so we'll finish that on Tuesday and then talk about EPR paradox. So let me just, with that as context, ask if there are any last questions on active versus passive transformation in Schrödinger versus Heisenberg. Cool. All right, Green's function theory. I know that I hated Green's functions when I was an undergraduate and perhaps through some part of grad school. I didn't really understand them. I feel like this is a nice way of understanding why they're valuable. And maybe you've already seen something similar to this, or you already are convinced that Green's functions are valuable. If so, this is just a nice refresher, maybe a slightly different way of thinking about things. So suppose I have an inhomogeneous possibly partial differential equation with boundary conditions, where I have some differential operator, which I call L sub x, acting on phi of x equals rho of x. So this should remind you of the Poisson-Laplace equation. I forget which of those is the inhomogeneous one, but I'm thinking about the inhomogeneous one with some boundary conditions on my function, which I might think of as a potential, is just 0. So we might think of some electrostatic problem where I want to know what the potential is, because if I find the potential, I find the electric field, and I say there are some sources which are rho, and I want the potential to go to 0 on certain boundaries because it's a conductor. If I can find a function g of x and x prime, and it's really a distribution. So it's really only well-defined up to integrating over sufficiently nice functions called a Green's function. Some people call it a Green function, kind of like the Legendre polynomial as opposed to Legendre's polynomials. You know, endless debate. So I'll call it a Green's function. Such that if I act this differential operator on this g of x and x prime, then I get a Dirac delta x minus x prime. And I act the boundary condition operator on g of x and x prime acting on the x argument, then I just get 0. Then the general solution phi of x to, okay, I'm going back to, again, equation 1. Is phi of x is equal to the integral over x prime g of x, x prime, rho of x prime. We'll call this equation 2. Right, so this is amazing. If I find, I need to prove to you that 2 is a solution to 1, but if I do that, then all I need to do for some potentially absolutely hideous partial differential equation with some unbelievable boundary conditions, so long as I find a Green's function that satisfies those equations basically 0 everywhere, with a sort of fairly modest boundary condition of what's happening when x equals x prime, then I'm able to find a solution given any distribution that anybody could possibly cook up. So it's incredibly powerful. So we can see that 2 solves 1 by direct substitution. So if I act the differential operator on phi of x, this is the differential operator acting on this expression. And the key point is that the differential operator is acting on x, while the integral is acting on the x primes. And so I can bring the operator through. This is the integral dx prime, Lx acting on g of x, x prime, rho x prime. So we can think about on the right-hand side, this differential operator acting on the whole integral. And then in the next line, the differential operator is acting only on the Green's function. And we know what the by construction result is. I guess I should actually call this 2 and call this 3. So this square bracket is delta x minus x prime by equation 2. The integral over x prime collapses the delta function, and this becomes rho of x, which is the first equation that we require. And then if we act the boundary condition on phi of x, what do you think is going to happen? Yeah, I'm not sure if like everybody's quiet because it's so obvious or because everybody's lost. But I'm sorry?
Yeah.
Yeah, it's 0, right? And is it, so yeah, so this is boundary condition acting on the same integral dx prime, gx, x prime, rho x prime. Boundary condition goes straight through the integral. And then this is just always 0. Again, by 2, you integrate 0 a bunch of times, you're going to still get 0. No matter how many times you integrate 0, you're always going to get 0. Now, if you're integrating something that limits to 0, okay, if you integrate it enough, you might not get 0. But if you're integrating actual 0, you're definitely going to get 0. All right, great. So any questions on Green's functions? That's really all I was going to talk about on that. Okay, great. So let's talk about retarded propagators So we defined the propagator so K, say X final, T final, X initial, T initial to be the matrix element of the time evolution operator. We define the retarded propagator, as the same thing, but with a theta function that guarantees that the final time is greater than the initial time. And I choose the word retarded purposefully because it's an analogy to the retarded Green's function, which you may have seen at some point in electromagnetism. I think I got a nod. Okay, well, in general, in electromagnetism, you're introduced at some point in your life, hopefully, with the idea of Green's functions and the idea that you can take initial conditions, like your initial distribution of charges, and propagate that to a potential at some distance away. Or you can think about electromagnetic waves. You can have some initial wave form that propagates forward in time, so you can then measure the future distribution of those waves. That is in contrast to the advanced propagator, which propagates you backwards in time. So you have some final, say, waveform. You ask, what is the initial waveform? So advanced and retarded tell you about whether you're propagating forwards or backwards in time. And here we're going to be propagating forwards in time. Yes. Correct. Yeah. So this is sort of the more natural Green's function where, say, you have some initial setup, some experiments with some initial conditions, and you'd like to predict the future measurements. Okay, good. So consider I partial t, oh, this is kr, sorry, I partial t, kr of x final, t final, x initial, t initial, except let's make this x and t. This will be my last derivation for today. So I partial t, x time evolution operator from t0 to t acting on x initial, and then theta function t minus t initial. So by product rule, I can bring the I partial t inside. I get I partial t time evolution operator, t initial, x initial, theta t minus t initial, plus x t initial, x initial, I partial t, theta t minus t initial. So here I have the Schrödinger equation. So x Hamiltonian at time t, t initial, xi theta t minus t initial, plus x t initial, x initial. And what is the time derivative of a step function? What's the derivative step function? Dirac delta, exactly. So this gives me a Dirac delta t minus t initial. Great. In the first line, my Hamiltonian is in principle a function of the x operator, the p operator, and t. I can pull this Hamiltonian operator through by, for example, inserting a complete set of states. And this is the Hamiltonian now where the x hat operator becomes the x, the p hat operator becomes a minus I partial x, and then I've got t, and then I have x time evolution operator, t initial, x initial, theta t minus t initial. And then in the second term, because I have this Dirac delta t minus t initial, this t might as well be a t initial. And then the time evolution from t initial to t initial is just unity. And then I get plus an I inner product of x with x initial Dirac delta t minus t initial. And so I have Hamiltonian x minus partial x minus I partial x t. This term here is just my retarded propagator again. X t x initial t initial. And then what's the inner product of x with x initial as a broad and ket? Yeah, exactly. So plus I Dirac delta x minus x initial, Dirac delta t minus t initial. And so I can rearrange things. And I find that my Hamiltonian as a function of x minus I partial x and t minus I partial t acting on my retarded propagator. Just give me 2 seconds and I'll be done. No, it's okay. I know I'm pushing things. Oh no. Well, this is the last line. So what I found is I have some differential operator, which is the time-dependent Schrödinger wave equation as a differential operator, acting on my retarded propagator is equal to Dirac delta of the arguments of the retarded propagator. So this is the proof that the retarded propagator is the Green's function for the time-dependent Schrödinger wave equation. So that was the statement that I want to get to. And yeah, cool. Thank you for giving me that extra time. So that's really where I think that's a reasonable stopping point. Well, we've got a few minutes left if you have any questions. Yes.
Is there a reason you didn't put an at on? Was that just, it's all.
Because it's an operator when it's hanging out inside of the inner product, but I'm moving it outside of that inner product. And so now it's a function of numbers and derivatives.
Okay.
Good. Let's hold off on the boundary conditions. But yeah, that's a good question. Yes.
Could you add another term with the function having Ti minus doing same for one
I'm not 100% sure I understand your question. So I could certainly do something where I define an advanced propagator where this is swapped.
Split up to and propagator to have two data functions.
And so say, hey, my propagator is this, which is this thing with a theta function TF minus TI plus theta function TI minus TF. You could, I don't know that there's much utility in that. So we're gonna want to work with Green's functions that correspond to physical setups that we're interested in. So in general, what you will find is that when thought about in the complex plane, the boundary conditions are associated with where the poles of the function live. And you know, with contour integration, if you close a contour and you don't close a pole, you get nothing. So depending on whether you push your pole in one direction or another, when you close a contour, you'll pick something up or won't. And that's going to be associated with, say, if I want to go forwards in time, I close my contour one way. If I want to go backwards in time, I close my contour in another way. And so that's why I'm pushing my poles one way or another. And we'll see that quite explicitly when we get to the resolvent, which is the Fourier transform of the propagator. And then this is leading towards, if you go into, say, field theory, then the propagator in field theory, you actually have two poles. So you can push both poles down, which is, I think, the retarded propagator. You push both poles up, and that's the advanced propagator, up to a minus sign to swap the two. And then there's the possibility you can shift the poles one up, one down, or the other way. And that's the Feynman prescription and the anti-Feynman prescription. So all of those propagators are valuable for calculating things within the context of quantum field theory. But for our purposes, where we're asking, how do I predict some future measurement given some initial conditions, I would like a retarded propagator. Good. Last questions. Okay. Stop. Thank you very much.